My queen, the hive structures are not responding to the Cerebrett's commands. There is no way to reinforce your warriors.
I'm remaking StarCraft Brood War from scratch in the Godot engine. Hey there, I'm Jusik, the Balkan developer, and I love making games and understanding how they work. Last time we managed to render a StarCraft map to the screen. I'm going to start working on the units next, but first I wanted to improve the map rendering. The first improvement that I did was to animate the water tiles. This was done by using a process called palette cycling. Last time we discussed that StarCraft doesn't store images as raw RGB values. Instead, for each pixel, StarCraft stores a reference to a color from a color palette. Palette cycling means changing the order of the colors to simulate motion of the pixels. We have only one frame in memory, yet we can simulate an animation. By changing the direction of shifting, we can change the animation. This is just one of many tricks with the palette that StarCraft uses.
You want a piece of me, boy?
We need to look at the units before we can make further improvements to the map rendering. For units, we will start by loading unit stats like hit points, mineral cost, damage, and so on. Unit stats are stored in .dat files, which are in essence a table in a database. The data is stored in column major format, meaning that we store entire columns in the file, one after the other. There are multiple .dat files and they point to one another. I wrote a script for passing each .dat file. Units.dat holds the unit data. Orders.dat holds the orders for the units. Upgrades.dat holds the upgrades for each race, and so on. Let's work on something more exciting, the unit graphics. StarCraft stores the unit graphics in GRP files. GRP holds multiple animation frames. Each frame is stored as an indexed image. The GRP file itself does not store a palette. This is important for later. The frames are compressed using run length encoding. Run length encoding simply stores how many times the same pixel color value appears in the image. If we have a long row of repeating pixels, we would encode them as the color index followed by the number of times the pixel appears on the row. This saves a lot of memory, making the files very small. GRP files are actually pretty simple. At the start, we have a header with the number of frames and the maximum width and height of all frames. Then comes a list of metadata, one entry per frame. Each entry in the metadata section gives us an offset when drawing the frame, the size of the frame, and where its pixel data starts in the file. Using the offset, we jump directly to the compressed frame data. Great, we could read the sprite data, but how do we actually draw it? There are a couple of options. First, we could convert the sprites into RGB images and render them as normal textures in Godot, but this uses a lot of memory. We would also need to convert everything up front, because doing it at runtime would be too slow. The second option is to draw sprites into a frame buffer. For each pixel, we look up its color in the palette and write that color to the pixel in the frame buffer. This is how StarCraft does it. However, this approach runs on the CPU, and in Godot that would be very slow. We want to make use of the GPU as much as we can. So instead, I went with a hybrid approach. We still use color indices and a palette, but we move the work to the GPU by using a shader. Shaders are scripts that run on the GPU for each pixel, and they determine the final color of the pixel. Here is how the shader works. First, we convert the color indices to a texture. We store the color index as the red value for the pixel. This gives us a red tinted version of the sprite. We draw this red version of the sprite using a Sprite 2D with the shader applied on top of it. We take the unit palette and we encode it as 1:256 texture, where each pixel is a color from the palette. When a pixel is about to be drawn, the fragment shader reads the red value from the sprite texture. That value is between 0 and 1, so we convert it back into a palette index from 0 to 255. We then use that index to read the correct color from the unit palette texture. The color we read becomes the final color of the pixel on the screen. So this is how we turn the indexed sprite into a full RGB image and draw it to the screen. Now you might notice that some parts of the unit are magenta. Those pixels are special. The areas of the unit sprite that reflect the player color intentionally use indices 8 through 15 in the palette. The unit palette contains a different version of these colors for each player. For easier access, I extracted those colors to a texture. The Y coordinate is the player index and the X coordinate is the color from the palette. So when drawing the unit, we simply replace the special indices with the colors from the player color texture. Changing the color of the unit is another visual effect that StarCraft achieves using the palette. Another trick is how it draws shadows. In StarCraft, shadows are also handled by swapping the palette. In my engine, I use a simpler approach. To draw the shadow, I just take each pixel and turn it into black with 50% transparency. The reason for this is that I didn't want to waste time and resources to load a palette that just turns the pixels black. I created a test scene that allows me to preview the sprites. I can search for a GRP by its name. The heading control allows me to change the direction the unit is facing. The frame set control allows me to view the individual frames of the animation in the facing direction of the unit. Finally, I can change the player color from this drop-down. Now that we can draw the sprites, let's see how they are animated. StarCraft uses a file called iscript.bin to define all unit animations. This file doesn't store images, instead it stores scripts that define how animations should play. Now, unless you want me to kill this Kakarot by playing its death animation and causing you to lose every single StarCraft Brood War game you ever play, like and subscribe this video. Each unit, or more precisely each image, is associated with an iScript entry. An entry contains multiple animations such as init, idle, walk, attack, death, and others. Each animation is a list of commands that the game performs. These commands include changing the current frame, waiting for a number of ticks, playing sounds, spawning overlays like muzzle flashes or explosions, jumping to other parts of the script, and so on. This makes iscript.bin more like a small scripting language than a simple animation file. In fact, it behaves very similarly to assembly code. Because of this, we cannot just read frames sequentially. We need to build a small virtual machine that keeps track of the current instruction, executes commands one by one, updates the sprite over time. This is exactly how StarCraft drives all of its unit animations. We know where to find the instructions and how to decode them, but to actually animate a unit, we need a small virtual machine. I created a component that handles playing iscript.bin animations. The component keeps track of which animation is currently playing, the current instruction pointer, how many ticks we still need to wait, and whether execution is running, stopped, finished, or is in an error state. Every game tick, the virtual machine reads the instruction at the current position, executes it, and moves on to the next instruction. Some instructions act immediately, like changing the frame. Others pause the execution, like the wait instruction. And some change control flow, like the go to or random conditional jump instructions. So instead of storing animation as timelines, StarCraft stores them as tiny programs that are executed over time. Now that animations are working, we can do one more improvement to the map renderer. To make the maps more interesting, StarCraft uses doodads. Doodads are decorations. Some doodads are static tiles, others are animated sprites. The static tile doodads are handled by the map renderer. For sprite doodads, we need to render them like units. When I tried to render the doodad sprites, two issues appeared. There seems to be a problem with the colors, and also the doodads are not animated. The first problem was resolved by using the terrain palette. To animate the doodads, I created a doodad scene and attached two components. The SC unit sprite component that draws the GRP images and the SC iScript component that plays the animations. That is all for now. Next time we're going to work on pathfinding. Don't forget to subscribe and turn on the notifications to not miss the video when it comes out. Peace, I'm out.